This is the video solution for exam 2 and dynamics. Okay, this first problem was an energy problem to try to understand what happens to this package. It's sliding along on this ramp, then climbs the wall, and we wanted to find out what happens when it gets up to point C here. Energy problem to say that we had 1/2 mv squared. We gain some mgh, and then we still have some 1/2 mv squared at the top. And so when we use that concept, we get the velocity at C is 24.1, and then it becomes a normal force problem. Sum of the forces normal is mass times acceleration normal to find out what the normal force is. To do that, we have to be careful to draw the free body diagram, and I took off points if you didn't draw a free body diagram, but in this case, at the top of the curve, the normal direction is pointing in. We have both normal force and the weight going down toward the center of the radius. So sum of the forces normal is mass times acceleration in the normal, and here's our equation. mv squared over rho, and solve for the normal force is equal to 52 pounds. The concept here was, one of the concept questions was, how fast does it have to go to stay in contact from here all the way to there? Well, unfortunately, it becomes a projectile as soon as it gets to the top, and then it will start falling immediately. So there's no amount of speed for it to, it can't go fast enough, I guess, for it to stay in contact and stick to the wall. That would be, or stick to the ceiling. That would be defying gravity. All right, so the second question is this energy problem with a spring, and here we just have beginning energy, which is 1/2 ks squared. All of that energy, spring energy, is converted into mgh when it climbs the wall or climbs the rod. Here it will have gained some mgh from here to here. It will have some speed, some 1/2 mv squared when it gets to the top, and it'll still have some spring energy when it gets there. So we had to find out the length of the stretch of the spring here, and then the length of the stretch here, and those are the two beginning conditions of the spring and the ending condition of the spring. And then what we're looking for is the 1/2 mv squared, and we get the V2. All right, this next problem is an impact problem. And the first, we had different versions of this impact problem, but in this one, the coefficient of restitution is 0, which means they stick together. So we have this object going this way, this one coming this way. When they collide, they stick together, and then they will go off in a common direction together. And so this is a conservation of momentum problem in both the x direction and in the y direction. In this case, we don't really care about line in the plane because they stick together. So we'll use conservation of momentum in both cases. So in the x direction, this one will have some mv, this one will have some mv, and so the common mv, or common velocity at the end of that, will be 0.72 in the I direction. If we look at the j direction, then we have a similar kind of thing where we have some beginning velocity in the j direction. This one has no velocity in the j direction, but after they join together, we'll have some mv in the j direction and then some common mv in the j direction. So in both cases, the ending momentum will be the sum of the masses times the common velocity in the x direction. Here we have the sum of the masses times the common velocity in the y direction, and we can get the actual speed and the actual direction. The actual direction is gained by looking at the two components. We have the 0.72 in the I direction, 2.56 in the j direction. We take the inverse 10, we can do that. Okay, and this next one is how much energy is lost in the impact. And the concept here is that it has some 1/2 mv squared at the beginning, so each object has their own 1/2 mv squared. When they collide, there's going to be some energy lost due to sound and deformation and that sort of thing. And so that's what is going on in this energy loss. And at the end of the problem, they have a common speed, a common mass, or all the masses together, and those together have some kinetic energy. So the difference in that is the loss of energy. In this next problem here, this was an impact problem where the coefficient of restitution had a value. E was equal to 0.3, and then they bounce apart if I have a coefficient of restitution greater than 0. So in this case, this one was stationary, this one was coming in at this speed, they bounce apart, and then this one will go in this direction, and this one comes back down in this direction. And what we have to understand is the line and the plane have different rules. So the line is the line connecting the mass centers. The plane will be perpendicular to the line. And so along the plane, we say VA plane 1, which is right here, is equal to VB plane 1 is equal to VB plane 2, which is coming down that way. And that value is 7 cosine 60. So that's going to be the same before and after for particle B. Particle A has no velocity in the plane, either before or after. So that's going to be 0 in both cases. The line, the coefficient of restitution and the conservation of momentum applies in the line. So the coefficient of restitution is that E is equal to VBL2 minus VAL2 VAL1 minus VBL1 in the denominator is equal to 0.3. Those are the two unknowns we're looking for. And in the denominator, we notice that this, if we call this our positive direction, then on the line, VB has negative velocity in the line direction to begin with, and that's what this negative is all about right there. And the negative times a negative is a double negative in the denominator. We get that equation for VB. And then for the conservation of momentum, we say that mv of this one plus mv of this one before is equal to mb v2 plus ma v2 in the line. And so that's what this combination is all about. And we get two equations, two unknowns. We put those together, and we can solve the line velocities. And then we combine the line and the plane velocities, and we get the actual velocities of each particle. So VA2 goes only in the VA2 when it smacks in here will only go in this direction. Can only go in the x direction, but VB has velocity both in the plane and the line, and so that's the actual velocity there. And then similarly, the loss of energy is the beginning energy minus the loss is equal to the ending energy where both particles are considered. This one is just a power problem where we have an mg sine theta, we have an ma, so the force at the wheels, and we say some of the forces in the x direction going up the hill is equal to the mass times acceleration in the x direction. So I got the force minus mg sine theta is equal to ma. Now what is the acceleration? That is given by the definition of the velocity. So a is equal to dv dt. Here we have v as a function of time. We can take that derivative and we see that acceleration is 5. The speed at the end of this thing is given at 10 seconds, so I just plug 10 in there and we get the speed is at the end of the problem is equal to 60 feet per second. So how do we solve the problem? We set up our force equation. Some of the forces in x is mass times acceleration in x. We see that the force at the wheels to make this thing happen, the maximum force at the is going to be 986.8. Well, actually, that is the constant force because both of these things are constant. And so that's 986.8 pounds. Then the power is equal to force times velocity. So the power at the wheels, force times the velocity of 60 feet per second. The power at the engine is equal to the power of the wheels divided by the efficiency. And I want it expressed in terms of horsepower, so I have to divide by our conversion factor of 550 foot-pounds per second per horsepower, and I can get that is equal to. Alright, this next problem is just boxes sliding down the ramp. I give this problem every semester, and so pretty soon we'll get it, I believe. But anyway, with this box is sliding down this ramp, this box is sliding down this ramp. They're both 5 meters high. Which one will get there the fastest? Well, this one, if it's frictionless, this one has a shorter path, so clearly that gets there the fastest. They both get there both have the same speed when they get down at the bottom, because mgh is equal to 1/2 mv squared. But the greatest energy comes from the greatest mass. So at the bottom I have 1/2 mv squared of this guy, and this has a bigger mass, so it has greater energy. The time comes from a couple of different things, but I used momentum if I could find the speed at the bottom. So I found the speed at the bottom of mgh is equal to 1/2 mv squared. Found the speed would be 9.9, and then I used momentum to say that I have a force going down the hill of mg sine theta, and that causes a change in velocity. So here's my momentum equation. The force down the hill is force times time, or the impulse down the hill is force times time. The only force is that mg sine theta, and I have a mass times velocity at the bottom, and I can solve that for this the time that it takes. Okay, this next problem is a conservation of momentum problem. Here the young man is on this cart, and he jumps from this cart and jumps into the air. And while he's in the air, he's going this way, cart A is going this way. Once they're separated, the cart A will continue to go this way. He will continue to go this way until he lands on cart B. So the first part of the problem is while he's in the air, we find out what the direction or the speed of cart A is by doing a conservation of momentum approach, where we have 0 at the beginning of the problem, 0 momentum. I got MVA1 or MVA2, and then we got MCV2 going this way. I don't know I got one equation with 2 unknowns, so I'll use the relative equation and plug that in, and I can solve for VA and VC. Now he's in the air, and then he lands on the other cart. And once he lands on the other cart, now they travel together. Now they're one unit, and they both travel in this direction. So we have the conservation of momentum, meaning his momentum at the beginning. Now we have both masses, and they travel together with a common speed after that. So that's what this conservation of momentum second equation is they got the mass of the boy, the speed of the boy. At the end of the problem, I have common mass and I have a common speed, or masses together with a common speed. All right, this last one was what is the peak speed? And we usually find that, or often find that, by finding the peak speed is where acceleration is equal to 0. So we sum the forces in the x is mass times acceleration in the x. I got a pushing force here. I got an mg and a normal force and a friction force. So the sum of those forces together, and minus mg minus the friction force, is when I set that equal to 0, I can solve this for the distance at which the peak speed occurs is going to be 2.114 meters. Putting that into an energy equation to find out the maximum speed, I can say that I have beginning energy of 1/2 mv squared. That was 1 meter per second at the beginning of the problem. There's no change in potential energy, no springs, and no change in gravity. But the U non is the pushing force minus the friction force, and the friction force is common, so I can just multiply it by the distance up here. The pushing force is a function of s, so I have to integrate that, and at the end of the problem I get a 1/2 mv squared. Solving all that, and I can see that I have once I solve this for velocity as a function of s, then I plug my s into this equation, and I can solve for the ending velocity.